The power beneath the city, how TurboGen pulse combustion technology becomes the energy spine of Citiwerx smart cities. Hello, I'm C. Cortland Hooper, PhD Chief Systems Integrator, and I'm pleased to share with you a strategic narrative of how the revolutionary TurboGen technology stack fits into the driver's seat and is the essential power driver and distributor of the Citiwerx digital platform and its other core technologies. Prologue. The problem no one has solved. Picture a city of 500,000 people that does not yet exist. It will be built from nothing, from bare earth on the outskirts of Bengaluru, India's Silicon Valley, engineered from the ground up to be intelligent, sustainable, and entirely self-sufficient. It will house families, power industries, grow its own food, recycle its own water, and generate its own energy. It will be a living organism, not just a collection of buildings. Now ask the question that every city planner eventually confronts. Where does the power come from? The answer that the world has defaulted to for more than a century is the centralized grid, a vast, aging, fragile network of transmission lines stretching across hundreds of miles, losing energy at every kilometer, vulnerable to weather, war, and the weight of ever-increasing demand. In India, where 416 million people are projected to migrate from rural villages to urban centers between now and 2050, that answer is already failing. The grid cannot keep up. The demand is too great, the infrastructure too old, and the centralized model too inherently brittle to serve a nation transforming at this speed. Something different is required, something smaller, smarter, more distributed, and more resilient. Something that puts the power generation where the power is needed, at the point of use, inside the city itself, embedded in its infrastructure like a nervous system rather than bolted on from the outside. That something is the TurboGen microgrid, and the story of how it arrived, what it does, and why it fits the Citiwerx smart city vision like a key into a lock is one of the most compelling convergences in modern engineering. Again, the world does not need a bigger grid. It needs a smarter one, distributed, resilient, locally powered, and intelligent enough to serve the cities of the 21st century. Part 1. The Science of the TurboGen. To understand what makes TurboGen genuinely revolutionary, you need to understand one thing about every combustion engine ever built. They all burn fuel the same way. Whether it is the engine in a car, a diesel generator, a gas turbine at a power plant, or a jet aircraft, the fundamental combustion process is identical. It is called flame front propagation, a wave of burning gas that spreads outward from an ignition point, like a ripple across water, converting fuel into heat and pressure. Flame front propagation works. It has powered civilization for more than a century, but it is inherently imperfect. The burning is uneven. The air-to-fuel ratios fluctuate. Heat escapes in all directions. The result is an engine that converts on average somewhere between 30 and 40% of the energy stored in the fuel into useful work. The rest, 60 to 70%, is wasted as heat, noise, vibration, and exhaust. The TurboGen does not use flame front propagation. Hypersonic combustion, the fundamental breakthrough. Instead, the TurboGen employs what its engineers call hypersonic, highly chemi-ionized combustion. Rather than a slowly spreading flame, the air and fuel react practically instantaneously, at hypersonic speeds, orders of magnitude faster than any flame front can travel. The combustion event is essentially complete before the gases have moved at all. The result is a far more perfect, far more controllable burn. What this achieves is remarkable. The air-to-fuel ratio, the lambda value in engineering terms, approaches theoretical optimum. In conventional engines, lambda values fluctuate constantly as the flame front struggles through the combustion chamber. In the TurboGen, combustion completes so rapidly and so completely that the ratio stays near perfect with every cycle. Less heat escapes to the environment. More of the fuel's energy is captured as usable exhaust gas pressure. More work is extracted per unit of fuel consumed. The result is thermal efficiency numbers that leave conventional generators in the dust. and a combustion architecture that has never before been applied to the challenge of distributed power generation. 3 parts, 1 moving part, 1 machine. The physical elegance of the TurboGen matches its combustion sophistication. The entire unit consists of just 3 main modules: a turbine module, a combustion module, and a high-speed electrical alternator module. The turbine module houses the rotor shaft with integrated magnetic media. The combustion module contains the proprietary combustion chamber, an aero valve element, a precision igniter, and a fluid-directing nozzle. The alternator module is a permanent magnet-synchronous machine that converts rotational energy into clean, regulated, noise-free, alternating current electricity. 3 modules, 1 complete power generation system, and, critically, only 1 moving part, the high-speed rotor shaft assembly. 1 moving part in an entire power plant. The implications of that fact are profound. Every failure mode in a conventional engine traces back to moving parts: pistons, valves, crankshafts, connecting rods, bearings, cam lobes. The TurboGen has 1 moving part. Maintenance requirements drop dramatically. Failure risk plunges. Operational lifespan extends far beyond what conventional generators can achieve. And the entire unit becomes small enough, light enough, and simple enough to be deployed almost anywhere. The pulse combustion cycle. The TurboGen operates on a pulsed combustion cycle that is conceptually related to the pulse jet engine, the same principle that powered Germany's Vi-1 flying bomb in World War II. But instead of producing thrust, the TurboGen harvests that pulsed energy to spin the boundary layer turbine rotor and drive the alternator. The cycle works as follows. The high-speed alternator's power electronics bring the rotor shaft up to operating speed. The boundary layer turbine rotor compresses incoming air, which fills and pressurizes the combustion chamber. Fuel is injected in precisely controlled quantities. The ignition device fires, triggering the hypersonic combustion event. The resulting high-temperature, high-pressure combustion gases are concentrated by the turbine nozzle and directed across the boundary layer turbine wheel, spinning the rotor shaft and generating electrical output. The cycle repeats continuously, breathing, compressing, igniting, expanding, in a rapid, efficient, rhythmic process that sustains itself as long as fuel and air are supplied. The key to the system's efficiency lies in the boundary layer turbine itself, a disc-type rotor that extracts energy from the viscous boundary layer of the flowing gas, rather than impacting blades as in a conventional turbine. This extraction method is inherently smoother, more efficient, and places far less mechanical stress on the rotor than blade impact designs, further extending the machine's operational life. Again, 1 moving part, hypersonic combustion, fuel-agnostic design. The TurboGen is not an incremental improvement on existing power generation technology. It is a different category of power machine entirely. Part 2. The wave disk engine, science proven, now practical. The TurboGen's pulse combustion architecture connects to a broader lineage of shockwave-based combustion science, a lineage that produced one of the most promising and most prematurely abandoned engine concepts of the modern era, the wave disk engine. Between 2009 and 2013, a research team at Michigan State University led by Dr. Norbert Müller built working hardware that demonstrated a thermodynamic principle called quasi-constant volume combustion. Funded by a $2.5 million ARPA-E grant from the U.S. Department of Energy, the wave disk engine used shock waves, not pistons, not flame fronts, to compress fuel-air mixtures almost instantaneously. In 2011, the team demonstrated 1 kilowatt of output at 7,000 revolutions per minute to Department of Energy officials. Theoretical thermal efficiency analysis suggested the architecture could reach 60%, nearly double the efficiency of conventional engines. Then the funding ended. The project stalled, not because the physics failed, but because 3 engineering problems proved too difficult with the manufacturing and materials technologies available at the time. Thermal management of the spinning disk. precision manufacturing of the radial channels that controlled shockwave timing, and lubrication of bearing surfaces operating at combustion temperatures where conventional oils carbonize. 14 years later, all three of those problems have been solved, not by new inventions, but by the maturation of technologies that were experimental in 2011 and are now commercially proven. Thermal management wave disk rotors possess an inherent self-cooling property. Each channel alternately passes cool, compressed air and hot, expanded gas dozens of times per second, faster than the metal's thermal response time, so the rotor never reaches equilibrium with peak combustion temperature. NASA research confirmed this enables operation at temperatures that would destroy conventional turbine blades. Thermal barrier coatings of yttria-stabilized zirconia, standard in modern jet engines, extend the thermal envelope further at minimal cost. Precision manufacturing. In 2011, the complex internal geometries of a wave disk rotor required expensive multi-axis CNC machining with tight tolerances that made production economics impossible. Metal additive manufacturing, laser powder bed fusion, now achieves dimensional tolerances of plus or minus 0.1 to 0.2 millimeters, with surface finishes that post-processing brings below 1 micrometer. Geometries impossible to machine conventionally are now printed routinely in aerospace-grade nickel superalloys. Oil-free bearing technology. The microturbine industry solved the lubrication problem 2 decades ago. Capstone Green Energy has shipped more than 9,000 microturbines using foil air bearings, completely oil-free shaft support systems that create hydrodynamic lift through a compliant foil structure. Their 30-kilowatt units operate at 96,000 revolutions per minute, with demonstrated mean time between failure exceeding 100,000 hours. No oil changes, no scheduled bearing maintenance, no contamination risk. This technology is now proven at commercial scale. The result is a class of shockwave and pulse combustion engines, of which TurboGen is the applied power generation implementation, that can realistically target 60 to 66% thermal efficiency in a package dramatically simpler and lighter than any piston or conventional turbine generator. No oil system, no cooling circuit, minimal moving parts, direct electrical output, and fuel flexibility that conventional generators cannot match. Fuel agnosticism, the strategic wildcard. Perhaps the most strategically important characteristic of pulse combustion and wave disk architecture is that it does not care what you burn. The same fundamental combustion chamber can be tuned to operate on gasoline, natural gas, biogas, bioalcohols, hydrogen, waste methane, or green CO2 sequestered synthetic fuels, with relatively minor modifications to the fuel injection and control systems. At 60 to 65% thermal efficiency on biogas, the methane produced by anaerobic decomposition of organic waste, a TurboGen-based power system produces approximately 5 to 10 grams of CO2 per 100 kilometers of equivalent energy output. That is a 90 to 93% reduction versus conventional gasoline generation. On green hydrogen, the life cycle emissions approach zero. On manure-based biogas using ISO system expansion accounting, the system can actually achieve negative net emissions, removing more carbon from the atmosphere than it produces. For a smart city that generates organic waste, treats sewage, and manages agricultural residues, as every Citiwerx township is designed to do, the circular economy implications are immediate. The city's waste becomes the city's fuel. The fuel generates the city's power. The power runs the city's systems. Nothing is wasted. Everything cycles. Again, the city's waste becomes the city's fuel. The fuel generates the city's power. The power runs the city's systems. This is not a vision for the future. It is an engineering reality available today. Part 3. The microgrid architecture. A single TurboGen unit, powerful and efficient as it is not the complete solution. The complete solution is the microgrid, a distributed power generation and storage system built around one or more TurboGen units, supplemented by solar and wind capacity, anchored by battery energy storage, and managed by intelligent power electronics. Understanding why the microgrid architecture matters requires understanding what is wrong with the alternative, the centralized grid. A centralized grid is, at its core, a long-distance transportation system for electricity. Power is generated far from where it is used, at coal plants, gas turbines, or hydroelectric dams, and then transmitted across hundreds or thousands of miles of high-voltage transmission lines to the point of consumption. Every mile of transmission wastes energy. Every transformer step-down loses a percentage. By the time electricity reaches a household from a distant power plant, the transmission and distribution losses alone have consumed between 6 and 10% of the original generation. In countries with aging infrastructure, those losses are significantly higher. And centralized grids are fragile. A single failure at a transmission hub can cascade across the entire network. A natural disaster, a cyber attack, or even a severe weather event can take down power for millions of people simultaneously. In a time of war or national emergency, centralized grids are strategic vulnerabilities of the highest order. Local power, local control, no transmission losses. The microgrid inverts all of this. Power is generated where it is consumed, inside the city, on the block, at the building level. There are no long-distance transmission losses because there is no long-distance transmission. The TurboGen unit powers the immediate community. Excess power flows to neighbors. The battery storage module absorbs generation peaks and fills demand valleys. Solar and wind capacity supplement the TurboGen when conditions allow, reducing fuel consumption further. The entire system is orchestrated by power electronics that balance generation, storage, and consumption in real time. A microgrid can consist of a single TurboGen unit serving a cluster of homes or multiple TurboGen units joined together to serve a larger community or industrial campus. Microgrids can be networked together, creating a resilient web of local generation nodes that share load and provide mutual backup. If any single node fails, its neighbors absorb the slack. The lights stay on. Microgrids are not stationary. The same architecture that powers a residential block can be containerized and deployed on a trailer, rolled to a disaster zone, plugged in, and operational within hours. The same TurboGen unit that heats water for a residential district can be reconfigured as a mobile charging station for a fleet of electric vehicles. Microgrid kiosks, standalone power generation units deployable like cellular towers, become a new category of infrastructure as familiar and ubiquitous as the smartphone tower. Cogeneration, 90% thermal efficiency. Perhaps the most remarkable efficiency achievement of the microgrid architecture is cogeneration, the simultaneous extraction of electrical power and useful thermal energy from the same combustion event. When a TurboGen unit generates electricity, it also produces substantial exhaust heat. In a conventional power plant, that heat is wasted, vented to the atmosphere as a thermodynamic inconvenience. In a microgrid configured for cogeneration, that heat is captured and put to work, heating water for residential use, contributing to space heating in cooler climates, or driving absorption chillers for cooling in tropical environments. With cogeneration, the total thermal efficiency of the microgrid system, the fraction of the fuel's energy that is converted to useful work, rises from the TurboGen's already impressive base efficiency into the 85 to 90% range. Nearly all of the energy in the fuel is used. Almost nothing is wasted. For a smart city that needs both electricity and hot water and thermal comfort for its residents, as every Citiwerx township does, cogeneration transforms the TurboGen microgrid from a power generator into a complete community energy system. Again, TurboGen delivers 85 to 90% total thermal efficiency through cogeneration. The TurboGen microgrid does not just generate power. It generates power, heat, hot water, and resilience simultaneously from a single fuel source. Part 4. Citiwerx, the city that thinks. Before we can understand how TurboGen fits into Citiwerx, we need to understand what Citiwerx actually is, because it is far more than a real estate development project. Huntington York Development Corporation is not building housing. It is engineering cities, complete, integrated, self-sustaining urban ecosystems designed from first principles to meet the demands of the 21st century. The Citiwerx platform is the digital and physical spine of those cities, a layered IoT architecture that connects every building, every utility, every resident service, and every infrastructure system into a single intelligent network that monitors, manages, and continuously optimizes everything it touches. The scale of the opportunity that Citiwerx is positioned to address is staggering. India faces a housing shortage of 93 million units by 2036. 416 million people will migrate from rural villages to Indian cities between now and 2050, the largest rural-to-urban migration in the history of human civilization. The government of Prime Minister Modi has committed to 500 new smart cities under the Smart Cities mission, with total infrastructure investment estimated at $1.5 trillion. And at the center of this transformation sits Bengaluru, named by Jones Lang LaSalle as the fastest-changing and most dynamic city in the world, where HYDC's Phase 1 Eco-Smart Village is shovel-ready, fully permitted, and waiting for construction financing. Citiwerx addresses this opportunity through 8 integrated city systems: next-generation green townships, intelligent water management, embedded renewable energy, vertical farming, carbon-neutral modern infrastructure, the Citiwerx digital platform itself, cultural and heritage integration, and the smart energy grid that ties everything together. Each system is not an add-on. It is core infrastructure designed in from the first day of master planning. The 8 pillars, and where energy sits. Water management delivers 20 to 40% efficiency gains through protected sources, closed-loop treatment, and continuous recycling. Renewable energy, solar walls, integrated wind turbines, and smart building systems progressively reduces dependence on external supply. Vertical farming produces food locally, eliminates food mile emissions, and turns organic waste into agricultural resource. The Citiwerx digital platform automates the economy of each township, delivering household and resident online services across every utility and amenity in a market projected to reach $500 billion by 2026 and $1 trillion by 2032. And threading through all of it, powering the water treatment systems, the vertical farms, the smart buildings, the EV charging network, the Citiwerx digital platform servers, and every home and business in the township is the energy grid. This is where TurboGen enters the picture, not as an external vendor, not as a supplementary technology, but as the fundamental energy infrastructure upon which the entire Citiwerx's smart city model depends. Again, Citiwerx is not a grid-dependent city waiting to be connected. It is an energy-sovereign city that generates its own power, manages its own resources, and improves its own efficiency as it grows. Part 5. The integration. TurboGen inside Citiwerx. The convergence of TurboGen microgrid technology and the Citiwerx Smart City platform is not coincidental. It is architectural. When you lay the requirements of a Citiwerx township over the capabilities of the TurboGen microgrid, the alignment is precise at every point. Application 1. The residential microgrid. Each residential cluster within a Citiwerx township, a block of homes, a mid-rise building, a neighborhood hub, becomes its own energy-sovereign entity powered by a TurboGen microgrid unit. The TurboGen generates the electrical power for the homes. The cogeneration heat exchanger captures exhaust heat and delivers hot water to every residence. The battery storage module absorbs midday solar generation and feeds it back during evening peak demand. The power electronics system communicates with the Citiwerx digital platform, reporting generation, consumption, and storage data in real time. Residents see their energy consumption on the Citiwerx app on their phone. The platform optimizes their usage automatically. When the biogas feedstock from the township's waste management system is abundant, the TurboGen runs at full capacity and stores surplus in the grid's battery network. When solar generation peaks on a clear afternoon, the TurboGen throttles back and the batteries charge. When demand spikes in the evening, both the TurboGen and the batteries respond simultaneously. The system is always balanced. The power never goes out. Application 2. Water treatment and vertical farming power. The Citiwerx water management system, with its protected sources, closed-loop treatment, and continuous recycling infrastructure, is an energy-intensive operation. Pumps, filtration systems, UV treatment, and distribution all require reliable, continuous power. The vertical farming operations that supply fresh produce to township residents require equally reliable power for lighting, climate control, irrigation, and nutrient delivery systems. Both of these critical systems are precisely the kind of baseload applications for which the TurboGen microgrid is optimized. Running at constant speed for continuous output, the TurboGen supplies the steady, reliable power these systems demand, while the cogeneration thermal output supports the climate-controlled vertical farm environments and the hot water requirements of the water treatment process. One fuel input, multiple useful outputs, every energy stream accounted for. Application 3. The waste-to-energy closed loop. Here is where the Citiwerx and TurboGen integration achieves something genuinely unprecedented, a closed-loop energy system in which the city's waste becomes its fuel, and its fuel becomes its power, and its power runs its systems, and its systems produce more waste, which becomes more fuel. Every Citiwerx township is designed for 100% waste-to-value management. Organic waste from residences, restaurants, and vertical farms goes to anaerobic digesters that produce biogas. That biogas, primarily methane, the same molecule as natural gas, feeds directly into the TurboGen combustion chamber. The TurboGen burns the biogas at hypersonic combustion efficiency, generating electricity and thermal heat. The electricity powers the township. The heat supports the digester process temperature and the water treatment system. The digester produces fertilizer as a byproduct, which feeds the vertical farms. The vertical farms produce food, which generates organic waste, which goes back to the digesters. Nothing leaves the loop. Nothing is wasted. The city is a closed thermodynamic system, consuming its own outputs, fueling its own operations, and continuously improving its resource efficiency as the population and the data systems that manage it both mature. Life cycle carbon emissions from this system, using ISO system expansion accounting for manure-based biogas, can actually be negative. The city removes more carbon from the atmosphere than it emits. A city that is not merely carbon neutral, but carbon negative. A city that heals its environment as it grows. Application 4. EV charging infrastructure. India's electric vehicle adoption is accelerating rapidly. Every Citiwerx township will house residents who drive electric vehicles and expect the charging infrastructure to match the quality of the homes they live in. But EV charging at scale places enormous demands on grid infrastructure, demands that an already strained national grid cannot meet. TurboGen microgrid units deployed as dedicated EV charging stations, either fixed installations within the township or mobile units that can be repositioned to meet demand, provide exactly the point-of-use charging capacity that the EV ecosystem requires without placing any additional load on the external grid. Fast charging at the parking structure level, powered by a TurboGen unit running on locally produced biogas, becomes a competitive amenity that Citiwerx townships can offer from day one. The same containerized microgrid architecture that serves a parking structure can be deployed on a trailer and positioned at a temporary construction site, a sports event, a disaster relief operation, or a remote township development phase where permanent infrastructure has not yet been installed. Mobility is a capability, not a compromise. Application 5. Grid independence and resilience. The Citiwerx Smart City is designed to be desirable precisely because it offers what conventional Indian cities cannot: reliability. Power cuts in India's existing urban centers remain a chronic problem. The national grid is under strain from demand that consistently outpaces generation capacity. For the technology professionals, business owners, and young families who are Citiwerx's target residents, people who work from home, run digital businesses, and depend on continuous connectivity, a power cut is not an inconvenience. It is an economic crisis. A Citiwerx township powered by a networked TurboGen microgrid system is genuinely grid independent. It connects to the national grid when that connection is advantageous, selling surplus power, for instance, when the township's generation exceeds its consumption, but it does not depend on the national grid for survival. If the national grid fails, the township's microgrid continues operating. The lights stay on, the water keeps flowing, the vertical farms keep growing, the Citiwerx platform keeps running. Life continues normally in a city that has insulated itself from the fragility of the infrastructure around it. This resilience is not just a quality of life feature, it is a fundamental competitive advantage in the Indian market and a core part of the value proposition that justifies Citiwerx township prices at premium levels above the surrounding market. Again, when the national grid fails, and it does and will continue, the Citiwerx township keeps running. That is not a marketing claim. It is a physics guarantee built into the microgrid architecture. Part 6. The Citiwerx digital platform and the intelligent grid. The TurboGen microgrid provides the physical power. The Citiwerx digital platform provides the intelligence that makes that power perform at its maximum potential. Together, they create something that has never existed before: a truly intelligent, urban energy ecosystem. The Citiwerx platform operates on a 7-layer IoT architecture that connects physical devices and controllers, communication networks, edge computing systems, enterprise data storage, abstraction and normalization layers, resident-facing applications, and business process automation tools. Every sensor in every building, every meter on every utility line, every actuator in every HVAC system is connected to this platform and reporting data continuously. Applied to the TurboGen microgrid network, this intelligence transforms raw power generation into a managed, optimized, continuously learning energy system. The platform knows, in real time, how much power each TurboGen unit is generating, how much each building is consuming, how much is stored in the battery network, what the solar forecast is for the next 6 hours, and what the township's biogas production is running at. From that data, the platform makes thousands of micro-decisions every minute. Ramp this TurboGen unit up, charge those batteries now, pre-cool these buildings before evening peak demand, route this surplus power to the EV charging cluster. Alert the operations team that this unit's thermal output is trending 2 degrees higher than baseline. Schedule a diagnostic inspection. The result is an energy system that gets more efficient over time, not because the hardware changes, but because the intelligence managing it accumulates data, learns patterns, and continuously refines its optimization. A Citiwerx township in its 3rd year of operation will be measurably more energy efficient than it was in its 1st year, even with identical hardware, because the platform has 3 years of data to learn from. This is the promise of the smart city realized at the energy layer, not a grid you plug into, a grid you grow with. Part 7. Development readiness and the path forward. The TurboGen microgrid is not a speculative concept. Its core components are engineered, tested, and supported by a robust global supply chain. Adapting it to Citiwerx will take less than a year. The high-speed, permanent magnet synchronous alternator, the electrical generation heart of the system, has been engineered, developed, and successfully tested at the 10-kilowatt scale. Multiple capable manufacturing vendors across the globe are ready to produce these alternators in volume. The power management electronics that control the entire system are available from internationally known manufacturers with demonstrated high-volume, high-quality supply capacity. The turbine housing, the the rotor shaft assembly, and the enveloping mechanical structure are straightforward engineering and manufacturing challenges with numerous available suppliers. The work that remains, and it is real work, not hand-waving, is the final design iteration of the combustion module and the computational optimization of the boundary layer turbine rotor for the specific performance requirements of the microgrid application. Engineering estimates place the time from final design drawings to a running bench prototype at approximately 1 year, drawing on the substantial prior modeling and bench testing that has already been completed. 1 year to a working prototype. From there, the path to commercial deployment follows the Citiwerx development timeline naturally. Phase 1 construction in Bengaluru begins in 2027, providing the perfect proving ground for the first operational TurboGen microgrid systems in a real smart city environment. Scalability, from 1 home to 1 million residents. The elegance of the microgrid architecture is that it scales without architectural change. A single TurboGen unit powers a residential cluster. Multiple units, networked together, power a neighborhood. Hundreds of networked units, managed by the Citiwerx platform, power a city of 500,000 residents. The same hardware, the same software, the same physics. Just more of it, connected more extensively, managed more intelligently. And when HYDC's 8-city rollout across Bengaluru, Delhi, Mumbai, Pune, Hyderabad, Chennai, Ahmedabad, and Kolkata is fully operational, housing 400,000 to 520,000 residents across 130,000 homes, the TurboGen microgrid network becomes one of the largest distributed energy systems ever built, not a grid serving a city that is its own grid. Beyond India, the Citiwerx franchise model, designed for deployment across India's 104 Tier 2 cities and then globally, carries the TurboGen microgrid with it as a core technology component of every township. Every franchise deployment is another TurboGen system deployed. Every new city is another proof point. Every proof point strengthens the case for the next one. Again, the Citiwerx franchise model does not just replicate the city design, it replicates the energy architecture. Every new township is another TurboGen microgrid deployment, scaling the technology as it scales the city. The little turbine that could, like the children's book about the little railroad engine that could, there is a myriad of things the micro-turbo technology can do beyond help power the smart cities of the future. Let's take a couple of minutes to explore. TurboGen second-tier applications. Future additional revenue streams may be produced from the manufacture and sale of this small sample. There can be targeted devices utilizing the thermal efficiency benefits of the pulse detonation combustion process. Small yet powerful devices can be created utilizing this breakthrough in high-efficiency turbo machinery. Turbo battery devices, the size and form factor of a typical mobile phone, can be created producing 50 watts to 500 watts of electrical power, and round disc-shaped units to produce up to 5 kilowatts of electrical energy to power small personal and household devices, such as personal computers, e-bikes, e-motorcycles, street vendor stands and food trucks, factory service trucks, utility support vehicles, garden equipment, city trams, hand tools of all kinds, camping equipment, audio equipment, etc. All applications utilizing detonation combustion engines with ultra-low emissions, a true revolution and a health benefit in population-dense contained city environments. Air conditioning power consumption is becoming one of the fastest-growing usages of electrical grid energy. Ductless systems are the dominant air conditioning format due to their simplicity of design and their ability to cool only areas that are occupied and actually require climate control. Individual turbo batteries can power individual ductless air conditioning modules for even more energy usage customization and energy savings. Over-the-road refrigeration trucks and stationary chilled storage units are another large energy-consuming area where the improved thermal efficiency of turbo battery generators can save costs to run these mobile and stationary refrigeration systems. Battery maintenance charging systems designed to keep conventional stored batteries at fully charged and ready-to-use state is another welcomed application for turbo battery power solutions. Additionally, these turbo batteries can top off battery-powered hand tools in field use conditions in order to keep them at fully charged service and avoid the need to switch out low readiness state batteries in the field and hence maintain hand tool productivity. Turbo batteries are designed to conveniently dock onto different size fuel modules using standardized, quick-release fuel supply fittings in order to better fit the application need. Turbo batteries are designed to use net-form manufacturing processes such as injection molding, net-shape sintering, and 3D printing. Turbo battery production will utilize fully automated component manufacturing and assembly machines. These small fuel-powered generators can also be ganged together to multiply a given power output requirement on demand. Small size, multi-fuel, take-anywhere power, and low manufacturing cost are major advantages with turbo batteries. Auxiliary power units, APU, TurboGen devices ranging from power levels of 1 kilowatt to 1,000 kilowatts. These compact-size electrical generators can be created utilizing the detonation combustion turbine architecture. These flex-fuel engine generators can be combined with battery or capacitor energy storage devices to provide clean and fuel-efficient power delivery. Able to power everything from industrial pumps to emergency backup generators for residential homes, TurboGen APUs are an industrial necessity in smart city design and planning. Automotive turbine drives. Utilizing the TurboGen APU solution, an automotive-focused drivetrain consisting of a suitable TurboGen APU combined with an electric motor, an efficient turbine electric drivetrain is created. No need to add a standalone battery module in vehicle to provide all system benefits of a pure EV. Installed into a lightweight and aerodynamic vehicle, a true 100+ miles per gallon vehicle can be created. With energy and emissions efficiency of the TurboGen APU, pure EV solutions will be hard-stressed to remain commercially viable at this performance level. Additionally, an APU-equipped vehicle becomes a useful mobile power plant, where if such a vehicle is parked next to a home or business, this vehicle can power these locations with full power capacity available. A smart grid city having these mobile generators operating nearby can provide very useful additional energy support to the smart grid infrastructure. Full battery electric EVs can integrate TurboGen APU systems and add battery charging capability directly on board of the EV vehicle. Charging can occur during a road trip or with the vehicle parked and not in use. Range anxiety is eliminated with this practical solution. No need to locate a charging station when traveling long distances in an EV vehicle equipped with a TurboGen. These are but 3 of over 100 additional applications on the drawing board of the core TurboGen Tesla-inspired stacked disk technology my partners and I have patented and which will be exclusively under the HYDC Smart Cities Citiwerx umbrella. Epilogue: when the technology finds its city. The history of technology is full of ideas that were right before the world was ready for them. The wave disk engine demonstrated 60% thermal efficiency in 2011 and disappeared because the manufacturing technology to build it reliably did not yet exist. Distributed power generation was proposed as an alternative to centralized grids for decades before the electronics to manage it became affordable. Biogas as a vehicle fuel has been technically viable for a century, but commercially marginal because the scale to make it economical was never assembled in one place. The TurboGen microgrid is the convergence point where all of those ideas finally find the conditions that make them not just technically possible, but commercially inevitable. Additive manufacturing has solved the precision production problem. Foil air bearings have solved the oil-free operation problem. Power electronics have solved the distributed grid management problem. And Citiwerx, building 130,000 homes across 8 Indian cities with a waste management system that produces biogas, a digital platform that manages energy in real time, and a resident base that demands reliability above all else, has provided the application environment that makes the economics work. When you stand in a Citiwerx township in Bengaluru in 2029, in a building that uses 40% less energy than a conventional structure, powered by biogas produced from the township's own organic waste, heated and cooled by a system that captures 90% of its fuel's energy, connected to a digital platform that knows exactly how much power you are using and where every watt is coming from. You will be standing inside the answer to a question that has been asked for 100 years. How do you power a city without destroying the planet? You build a city that powers itself. That is the TurboGen microgrid inside Citiwerx. That is the convergence of engineering and vision that Huntington York Development Corp is now positioned to deploy at a scale the world has never seen. The power beneath the city is finally ready to light it up.